And welcome back to chemistry. Now, looking at this phase diagram on the left here, you see between purple and brown, between the liquid and the gas, you follow the boiling point line up and to the right, increasing pressure, increasing temperature. It ends in a dot known as the critical point. What is that? Well, moving now on to the next slide, that is the critical temperature. Okay, that is the temperature at which the distinction between liquid and gas ceases to become meaningful. Or to put it another way, the temperature has gotten so high that no matter what the pressure is, you can't really get it down to a liquid anymore. Except that's not really true. You know, if you have an incredibly hot, incredibly dense material, it's still going to be a fluid. What happens when you look at the fluid itself, though, is that as you follow that line, you know, the boiling point line, you know, where you have equilibrium between liquid and gas, you'll always see a distinct boundary between the two. You know, that line means they're existing at equilibrium. You know, both phases exist. So you have a sealed container where you can manage temperature and pressure carefully. You move upward and to the right along that line. You'll always see the boundary. You know, there's the liquid on one side, there's the gas on the other, until you get to the critical temperature. The boundary will sort of get fuzzier and fuzzier and then disappear. The two phases have become one. It's called supercritical because the material you'll have there is a sort of, it's kind of partway between liquid and gas. You're at very high pressure, very high temperature. The distinction between the two has become meaningless. You know, that's why there's no longer the phase boundary. So it's just that the particles are much further apart than you would expect for, well, not much further, but they are further apart than you would expect for liquid. They're much closer together than you would expect for gas. They're moving ridiculously fast. It's a very high energy system. It's a very strange sort of condition. And supercritical fluids, they can be very interesting. They can have interesting properties when it comes to what they can dissolve, the way they behave with certain sorts of metals or non-metals, things like that. So it's a very interesting field of study if you want to go into some sort of materials engineering. The other thing on this slide here is we're talking about supercooled fluids. This is sort of with respect to glass forming materials. We'll talk about that in a little bit when we get to solids. A supercooled fluid is what you get when you cool a liquid down below the melting point. I call it the melting point there, not the freezing point, for a very simple reason. Melting, you know, the physical process of melting involves particles of a solid, you know, molecules or atoms, particles of a solid spontaneously leaving the solid and entering the liquid phase. You know, they sort of detach from the solid structure and they're able to move freely. And any individual particle can do that. There's no flaw about that. There's no reason for it not to do that. It can do whatever the hell it wants. But the reverse is not true. You cannot have a single particle of a liquid suddenly decide, okay, I'm a solid now. Being a solid requires the association of multiple particles in the form of that solid structure. And an individual particle just, it can't do that. So there are two processes that take place when you form a solid. The first is seed formation, or nucleation, as it's sometimes called, where you have a small number of particles come together to form the nucleus, the core, the smallest possible portion of the solid. And the other phase to forming a solid is crystal growth, when, you know, other particles leave the liquid and attach themselves to the surface of that solid. If you've ever seen videos of crystallization happening. You can sort of see that happening. It sort of starts at one point and spreads out from there. It can be fairly beautiful. So the thing is that the process of nucleus formation or nucleation, the formation of those initial seeds, is very difficult. Remember, I've talked about boundary effects, the fact that things at surfaces, at edges, are unhappy. Well, that crystal nucleus, the solid seed there, is all surface. It's very difficult to get those started. So that occurs at a very low temperature. The crystal growth, however, is much easier because you have the solid core there started. And all that has to happen is nearby particles of the liquid decide that they would rather be attached to that solid surface. It's much easier. But they have to be able to move for that to happen. And so the crystal growth phase occurs at a higher temperature than crystal formation, or the seed formation, the germination. So those are the two phases, and they both have to be at lower temperatures than the melting point. The melting point is when the particles will spontaneously leave and enter the liquid. So below the melting point is when they have to happen. And so you almost always do technically, go below the freezing point, or the melting point, I should say, a little bit in order to get the freezing process started. We're not going to go into detail about glass-forming materials. I could go on way too long about those. But I just wanted to let you know a little bit about that. That every time you freeze something, you're technically making a supercooled fluid. You're going down into the region below the melting point. The liquid wants to be a solid, but there is what's known as a kinetic barrier. It's difficult for the particles to actually arrange themselves in the correct way in order to form the solid that they want to be. You can think of it in terms of the reaction, like there's the activation energy. You have to provide that initial spark to get the fire started. Well, the kinetic barrier is sort of similar, except that instead of an amount of energy that it needs to get started, it needs a physical arrangement of things before it can get started. Some materials are better able to be supercooled than others. Water is terrible at it. Water is a liquid with a lot of structure in the liquid phase. So it's very, very difficult to supercool water more than just a small, tiny, itty-bitty fraction of a degree Celsius. But something like glycerol, it's very easy to get that to supercool and to get it to be a liquid below the melting point. In fact, it's very, very difficult to get glycerol to not be a liquid below the melting point. All right, so that is supercritical and supercooled fluid. Let's move on to solids. So, solids, we're going to divide those up into largely just the two varieties. A crystalline solid is any solid that has a regular repeating structure inside of it. It's a three-dimensional structure. Semiconductors, metals, salts, ceramics, these all tend to be crystalline solids. They have some sort of pattern inside of them. They're a 3D quilt, as it were. The other kind is amorphous. That's Greek, means unshapeful. Morph means shape. A means not. So amorphous means without a shape. There's no internal structure. Glasses, rubbers, and plastics, the differences between those are kind of technical, but they all lack that internal structure. They have an unordered internal structure, or not even necessarily structure. They're solid, they just don't have a pattern. So technically, cheese is a plastic, and when you melt it, it's a rubber. Butter, likewise, is a plastic, and you get it warm and it turns into a rubber. The thing about amorphous solids is that they don't really have a well-defined melting point in the same way that crystalline solids do. But I definitely don't want to go too much into that, so we're going to go ahead and leave it there. And we're going to continue talking about solids by looking at the unit cell. Now, the unit cell is just the smallest repeating part of a 3D structure. So, in order to help understand that, let's retreat down to just 2 dimensions. Imagine you have a square. Then all you have to do you can cover an entire 2-dimensional surface with that square. You just repeat it and repeat it and repeat it, and you can cover an infinite plane with that square. So what if you don't have just a blank square? What if you have a square with a hypercycle or a hypercycloid drawn on it, like this one? Okay. Well, what happens when you repeat that is you see that that's not necessarily a hypercycle. It is a circle that is shared between 4 different squares. Okay. So, you have an infinite number of squares, you have an infinite number of circles. Each circle is shared between, 4 squares. Each corner of a square has 1/4 of a different circle. Okay. The unit cell gives us the same sort of thing, only in 3 dimensions. So here we have our unit cell with a sphere, that is to say an atom or an ion, located at each corner. How many cells is that sphere shared with? Okay. Well, let's go ahead and move it over to the side and see if we can't draw as many cubes as possible meeting at a corner, sharing that one sphere. Okay. So here's the corner is there at the middle of these 3 axes. So let's go ahead and sketch in 1 cube down here at this portion of that space. And then we sketch in another cube, sort of catty corner to it. So we have 2 cubes, and hopefully you can see that there should be 2 more, sort of in the empty spaces that I've left there. And hopefully you can see further still that leaves us with 4 more, above those, okay, giving us a total of 8. 1, 2, 3, 4 down at the bottom, and 5, 6, 7, 8 up top. Which means that when you look at the unit cell, when you look at the number of cells that an atom is shared between, there are 8 cells. Okay, every corner meets a total of 8 cubes, 8 cells, and or another way of putting that is that each sphere is shared between 8 cubes, sort of like one circle was shared between 4 squares. Another way of putting it is that there are 8, 1/8 of each. The sphere at the corner. There's 1/8 of the sphere per corner. Okay, there, that's the way I wanted to say that. But there's more ways to be inside of a cell than just sitting on the corner of the cube. Now I know I'm running up on the 15-minute mark, so hopefully you'll forgive me if I go a bit over. But there are other ways of sitting on, being shared, I should say, between unit cells. Okay, first up, we have an atom sitting on the face of a cell, an atom sitting on the edge of a cell, or an atom sitting on the interior of a cell, sitting inside of a cell. Now, we already looked at the corner case, and we saw that it was shared between 8 cells, or 1/8 sphere per corner. Okay. So let's go ahead and take a look at the edge case. Okay. So if we start drawing our edge, and we allow for multiple cells being around it, let's go ahead and fill out 2 of those cells. And we see that this is sort of like half of what we had before. You know, we have 2 cells sitting here, and we have 2 more cells sort of missing in the space in between them, for a total of 4. So if a sphere or an atom is sitting on an edge, then it is shared between 4 cells, or it contributes 1/4 of a sphere to the interior of that cell that it's in. Next up, we have the face case. That's a little bit easier. We just draw 2 cubes sitting next to each other. Okay, that one atom can only be shared between 2 cells if it's sitting on a face. So it contributes 1/2 of a sphere to the cell that it's sitting inside of. Finally, if the atom is sitting entirely inside the cell, then it's entirely inside the cell. It isn't shared with any others. So one atom inside is one atom inside, and it contributes 1 sphere to the interior of that atom, or 1 atom, to the interior of the cell. Okay. So those are the 4 possibilities for where a sphere or an atom can be located in a unit cell. It can be located on a corner, it can be located on an edge, it can be located on a face, or it can be located inside the cell. And if it is, it will contribute some fraction of the entire atom, 1/8, 1/4, 1/2, or 1 whole, to the number of spheres inside that unit cell. And so that is that's what we're looking at here, is we're trying to figure out how many atoms or ions are inside the unit cell based upon where they are located on the unit cell. Okay. And so when we return next time, we are going to look at different kinds of unit cells.